Alright, so you're working Poisson distribution problems, and you see they have a crazy formula. The hardest thing to figure out is going to be the average, the lambda here. Alright, however, we can use the tables to give us these answers. So, for example, if I know that the average is 5, which I figured out in this problem, and I can go here to table F, and look at these lambdas here. They go up 0.2, 0.02, 0.03, 0.04. We got to go all the way to 5.0. Alright, so here is 5.0. So if the average is 5.0 and the x in our problem was 0, it was a probability that no one used that ATM. We got 0.0067 whenever we rounded that in at 4 places in the calculator. Alright, well, 0.0067, that's it. Alright, so then the second problem we worked was what's the probability that in a 15-minute interval at least 3. And again, you can't really work at least 3 because 3 people could use the ATM, or 4 or 5 or 6 or 7 or 8 or 9 or 10 or 11. It could go on and on and on forever. So you have to use the complement. You say 1 minus the probability x equals 2 plus x equals 1 plus x equals 0. This is the same problem, so lambda is the same. Alright, so we look at lambda equals 5, and then x equals 0, 1, and 2. So here is, I don't know why it's an off there. So we go to 5. Here's 0, 1, and 2. So yes, you could probably take and add all these up and get the same answer, because eventually it goes to 0, 0, 0, 0, but there is some numbers out there. But use the complement. Say 1 minus the sum of x equals 2, x equals 1, and x equals 0. Add those 3 together, subtract it from 1, and you will get the answer. Now, if your lambda is something different, notice this doesn't go up by 0.1. If your lambda or your average is something different, then you're going to have to do it the long way. But as long as you can figure out your average or your lambda in the problem, and you know what your x is equal to, you can use this table to work the problem out a lot faster without having to do those calculations by hand.